So I thought it would be beneficial if we took a look at an activated sludge design problem. We've done all of this kind of a problem, but in separate little pieces during class. I thought it would be interesting and helpful if we just did one problem all the way through designing an activated sludge system. So to do that, what we're going to do is start out with a hypothetical problem, and let's look at the problem description. Let's suppose that a developer has proposed making a new development out in Goshen, Utah, which is at the southern end of Utah Lake. And in this development, they're going to have a large residential area, and then they'll have a small commercial and retail area also that'll service the community. It's kind of interesting a little bit. At one time, a development like this was proposed. I don't know where it is right now or if it's really going to happen, but there was one proposed at one time. So after the area was planned, the developer estimated that the wastewater flow rate from the development when it was built out would be about 750,000 gallons a day of wastewater, and that wastewater would be just a typical domestic type wastewater. So the owner decided that what they would need to do was to build a wastewater treatment plant to take care of all this wastewater because there's no treatment facility anywhere near there. And they would discharge to a stream that goes from the Goshen area down up into Utah Lake. So they went to the Department of Environmental Quality at the state and applied for a UPDES permit, and after some negotiations, the limits that they receive for their permit are listed here, where you can see that they need to have no more than 20 grams per cubic meter of BOD5 and no more than 20 grams per cubic meter of suspended solids at their treatment plant. So because the clarifier at these treatment plants doesn't work perfectly, in fact, some biological solids are going to escape from that clarifier, and when those solids escape, they're also going to exert some BOD. So we need to account for that when we design the treatment plant. That means we can't really design for that allowable effluent of 20 grams per cubic meter. We have to assume that there's also going to be some BOD added from the suspended solids that are found after the clarifier. And let's suppose that we assume that the maximum allowable concentration of suspended solids comes from that clarifier, and up above that stated that we can have no more than 20 grams per cubic meter. So let's assume that they have 20 grams per cubic meter coming from that clarifier, and that 65% of those suspended solids will exert BOD. So basically the BOD exerted by the solids is 65% of the solids concentration. So now the design BOD concentration that we need to use is the BOD5 that's allowable, which is stated above as 20 grams per cubic meter, and then we need to subtract off the BOD that comes from the suspended solid, so that's going to be 0.65 times 20. So when we do that calculation, we see that we really need to design the system for 7 grams per cubic meter as opposed to the 20 grams per cubic meter which the permit allows, because if there's 7 grams per cubic meter of BOD in the effluent coming into the clarifier, and then some solids remain in the clarifier after that, then we'll be right at 20 grams per cubic meter. So let's suppose that your firm was hired to do the job of designing this treatment plant, and that your boss has decided that it would be great to have a CSTR activated sludge plant. That would be the best thing to do. So you're kind of in charge of doing that design. So here's a figure that we're going to use that kind of describes this system. You can see all the symbols that we're going to use here, and you'll notice that we have a complete mixed aeration tank and a settling basin. We have a return sludge flow line, and then we have a waste activated sludge line also. You can see that we're wasting the mixed liquor well, we're not wasting mixed liquid, we're actually wasting settled solids, X sub R, the solids that have thickened at the bottom of the clarifier. Okay, so we don't have any wastewater as we begin this test, so we can't go and test it and determine what the growth parameters are for this wastewater. But we assume that it's going to be just a typical domestic wastewater, and that means that we can use just the typical wastewater growth constants for a domestic wastewater. And in your textbook, if you look at table 8-10, those parameters are listed, and you can see them listed here. K sub S is 60 grams per cubic meter of BOD5. K sub D is 0.1 per day. Mu max is 3 per day. And Y is 0.6. So the first step in the design of a treatment process like this is to determine what's the appropriate solids retention time, or mean cell residence time. We'll use the symbol theta C to represent that. And we developed this equation in class that says the effluent concentration from this treatment process would be equal to the equation that you see here. So if we substitute the values we know into this equation, you can see, first of all, we want our effluent to be 7, as we talked about on the previous slide. And we know everything else in this equation except for the mean cell residence time. So we can solve that equation for the solids retention time, or the mean cell residence time. And when we do, we find that we need to have a solids retention time of about 4.68 days. Now, as it ends up, I've worked with these kinds of things for a long time, and that's a real typical kind of a value that you might actually see at a treatment plant like this. So we can say, yeah, that sounds good. Now, you guys, having not had experience with this, wouldn't really know, so just check your calculations. Okay, well, the other mass balance equation, or mass balance that we could do on this system, would result in this equation. This equation we can rearrange to look like this. We've just moved the T sub 0 over to the left-hand side. And T sub 0 is the hydraulic retention time. Now remember, there's a difference between the hydraulic retention time and the solids retention time. They are not dependent on one another at all. They're independent variables. So the hydraulic retention time is the average amount of time water spends in the system, and the mean cell residence time is the average amount of time that cells spend in their system. And depending on how we operate the clarifier, we can keep the cells in there as long as we want them, independent of how long the water stays in the system. But if we look at this equation, one thing we'll see is the two variables on the left-hand side, x and t sub 0, are unknown. So there's two unknown equations, or two unknown variables in just this one equation. So on the other side of the equation, the right-hand side, we know the value of all those variables. So if we substitute in, we'll get this. And what we see is that the x times t0 needs to be equal to 222.8. Okay, now, as we said before, both of those variables are unknowns. So what that means, as a designer, I have a choice. I can pick whatever values I want for those two variables, but their product has to be 222.8. So if I pick an x value, I know what t sub 0 has to be. Or if I pick a t sub 0 value, I know what x must be, because those two multiplied together need to be 228. Now, the typical range for x values in a problem like this is between 1,000 and 3,000 grams per cubic meter. And that's just kind of typical values. So we also know that T sub 0 has an effect on the size of the system. If we have T sub 0, when it's small, the physical size of the reactor is going to be small also, and a smaller reactor is easier to design. So we have to remember that if we pick a really big X, then I can have a small T sub 0. If I pick a small T sub 0, I have to have a large X, conversely. So let's just choose a value right in the middle of that 1,000 to 3,000 and choose X equal to 2,000. Now remember, X is the mixed liquor volatile solids volatile suspended solids concentration for the system. Okay, so it's kind of the concentration of microorganisms in the system. So if we pick x as 2000, that means t sub 0 is going to be 0.1114 days, or 2.67 hours. So the hydraulic detention time in our aeration basins is going to be 2.67 hours. Okay, so now since we know that the hydraulic residence time is equal to the volume divided by the flow rate, I can calculate the volume of the reactor that's in this system. So just rearranging that equation, I know the volume is equal to the hydraulic retention time times the flow rate. So our hydraulic detention time is 2.67 hours and our flow rate is 118. So that means the volume of this reactor needs to be 316 cubic meters. So now we know the volume of the reactor in the system. Now, once we know all these things, one parameter that's commonly calculated when we look at an activated sludge system is the F to M ratio. And remember, the F to M ratio is the amount of food coming into the system divided by the quantity of microorganisms in the system. So the food coming in is just the flow rate coming in times the concentration of the BOD in the influent. And then I'm going to divide that by the mass of cells in the system, which is just the volume of the system divided by or multiplied by the concentration of the organisms in the system. Now you notice here that the influent BOD is listed in this equation as 123.5 grams per cubic meter. And where did that number come from? Well, that number came from, we assume this is a medium strength wastewater, and our medium strength wastewater would have an influent BOD of about 190, as you've seen earlier. But we have preliminary treatment and primary treatment before we have our activated sludge system. And in primary treatment, we're going to remove about 35% of the BOD. So 1 minus that 35%, or 65% of 190, is 123.5 grams per cubic meter. So that's why we use that 123. So that makes the food to microorganism ratio then for this particular system 0.55, which is a pretty good value for a typical activated sludge process. So another thing that we want to do is to calculate the waste activated sludge flow rate. And we're going to, or that's Q sub W. To do that, we're going to go back to our definition of the mean cell residence time. And we know the mean cell residence time is the mass of cells in the system divided by the mass of cells that are wasted from the system each day. The mass of cells in the system is just the volume divided or multiplied by the concentration. And the mass of cells that are wasted are just that waste flow rate, Q sub W, times the concentration in the waste. And if you remember from our little definition figure of our system, we're wasting from the underflow of the clarifier, or from the activated sludge recycle line. So our concentration there will be X sub R. Now we can rearrange that equation to solve for the waste activated sludge flow rate, Q sub W. When we rearrange it, it looks like this. Substituting our known values in, we find that the waste flow rate is about 13.5 cubic meters per day. But that's based on a specification for what the recycle or the return activated sludge concentration is, X sub R. In this case, we just assumed it to be 10,000. What that means is we have a choice of what that number is going to be, but we'll have to design the clarifier to give us the value that we've chosen. So we've got to choose a value that's in a range that's going to work, and typically it's going to be, it has to be greater than X. And the greatest it can possibly be is probably about 11 or 12,000. So 10,000 is on the high end, but I've chosen 10,000 here. Then we just have to recognize we designed the clarifier so that I can get 10,000. Now, the next thing that we want to calculate is the return activated sludge flow rate, Q sub R, and this is the equation that we can use for doing that. Um, we need to notice in this equation that we're using a little different parameter than we had before. We have x prime and x sub r prime, and these values represent, the prime means we're looking at suspended solids concentration rather than volatile suspended solids concentration. And you'll notice here when I put the numbers in, I didn't make any difference. I said x prime is equal to x and x sub r prime is equal to x sub r. And you know, typically you'd want to be a little bit more careful than that when you did this, but in this particular case, we're just trying to get Q sub r so we can see how large the flow is and size a pump for it. And so we don't need to be 100% accurate. And x prime and x are close enough to one another that I can just use them interchangeably. So I put the variables in, and what I end up with then is that x sub r is going to be about 685 or 686 cubic meters per day, or about 29 cubic meters per hour. Oftentimes we compare Q sub r to the actual influent flow, and our influent flow is 2,839 cubic meters per day, and so we take the ratio of those two, and this is commonly called the recycle ratio. We see that it's about 0.242, which means about 24% of the flow rate that's coming into the plant we're recirculating back into that original reactor. Okay, now the next thing I need to know, or that I'd like to find out about the system, is what quantity of sludge is going to be produced that I'm going to have to deal with. So to do that, I need to use the observed yield. So the yield, y, that's given in our problem is what we call a theoretical yield. And it's based on the assumption that organisms are not dying and decaying in the system. But we know they are. So we can account for that using KD and the mean cell residence time of the system to calculate what we call the observed yield, which is the actual yield that we'd measure if we went out to the process and measured it. So the observed yield is the true yield divided by 1 plus KD theta C. So in our case, the theoretical yield was 0.6, y. We'll divide by 1 plus KD, in our case, is 0.1. And remember, our theta C we calculated to be 4.86. So the observed yield is 0.4087. Okay, now the observed yield should always be a little bit less than the actual yield, and you can see in this case that it is, so I can assume my calculation was pretty close, or at least I probably didn't make any errors doing the calculation. So now the quantity of sludge that's being produced is the observed yield times the amount of BOD that's used up. Okay? The amount of BOD that's used up is the flow rate times the difference in the BOD concentration coming into the system and leaving the system. Okay, so in this particular case, our observed yield was 0.4087. Our flow rate is 2,839 cubic meters per day. And remember, coming into our activated sludge system, the BOD is 123.5. And leaving, we've designed the system so that it's going to be 7. Okay, so that means that we're producing 135.1 kilograms of solid material every day in the system. And that solids in the form of microorganisms. So it's microorganisms that we've created. Now, since that's how much that's being produced every day, it's also the amount that I have to waste every day so that I remain at steady state. So my waste, the amount that I'm wasting every day needs to be 135.1 kilograms every day. But remember, when I waste, I'm not wasting 100% solids. I'm only wasting, remember, that 10,000 milligrams per liter, which is 1% solids. So this 135 kilograms is the solid material that's in a much, much higher mass of total sludge because it's basically 99% water. But there's only going to be about 135 kilograms of solids that are in that waste that I get rid of every day. Okay, now the next thing that I need to know, and really kind of the last thing I need to know about this system, is how much oxygen is going to be required to make this thing work. This is remember, the expensive part of the system. And I have to supply as much oxygen to the system as is being used up by the microorganisms that are using the BOD in the system. So the amount of oxygen that I have to put in there is kind of equal to the amount of BOD that's exerted in the system. But remember, we said there's an interesting thing that happens here. If I eliminate cells from the system before they degrade, they haven't exerted a BOD. So if I grow a bunch of cells and then get rid of those cells, they never exerted a BOD, and that lessens the demand for oxygen the system has. So the demand for oxygen the system has is the amount of BOD that's used up minus 1.42 times the amount of solids that are created and that I waste. Okay, remember that 1.42 says that every 1 gram of cells that I waste would have required 1.42 grams of oxygen to be put in the system. But since I wasted them, I didn't have to. So the mass of oxygen that's required is Q times S0 minus S divided by F. Why is that F in there? Well, the F is in there because that 1.42 times P sub X, that's telling me an oxygen demand based on ultimate demand. I don't know if you remember when we developed that 1.42, but we actually did like a theoretical chemical equation that showed the complete destruction of cells into CO2 and water. Okay, and that's basically the theoretical or the ultimate oxygen demand. So the S and S0 are based on BOD5s. So what I've got to do is convert the BOD5 to the ultimate BOD. And what we've found out is that that conversion with domestic wastewater is right around 0.68. So in other words, what we're saying is if I divide the BOD5 by 0.68, that'll give me the ultimate BOD. Okay? So Q then is 2839, S0 is 123.5, S is 7, divided by 0.68, and then we're going to subtract off 1.42 times the quantity of cells that we waste every day, which we just found up above, P sub X, was 135.174. So solving that, we see we're going to require 294 kilograms of oxygen per day. Okay? Now, where's that oxygen going to come from? We're not going to put, elemental oxygen in the system or pure oxygen. We're going to just take atmospheric air and bubble it into the system. So I know that air has a density of about 1.185 kilograms per every cubic meter of air, and that there's about 23.2% oxygen by mass in atmospheric air. So knowing those two things, I can convert this 294 kilograms of oxygen to how much air would have that much oxygen in it. And as it ends up, it would take about 1,071 cubic meters of air to give 294 kilograms of oxygen. So that's how much air, and that's how much air we'd need if every little bit of oxygen in the air that we bubbled into the system went into the water. Unfortunately, it doesn't work that way. Remember, we talked about how oxygen's only sparingly soluble in water. So when we take a bubble of atmospheric air and it bubbles up through our aeration tank, not all of the oxygen in that little bubble is going to go out into the water. Some of it's still going to be in the bubble when it gets to the surface. And in fact, what we found is that at about the most efficient that we can get is maybe 8 to 10%. So if I assume that my aeration system's 8% efficient, we can divide that 1,071 cubic meters of air by 0.8 and see that it's going to take about 13,387 cubic meters of air per day to be blown through our aeration system. It's a lot of air, and it's expensive to do that, and that's why it's pretty important for us to be able to calculate how much that we need. And that'll also allow us to size blowers and the pipes to blow the air around and size all the different components of our aeration system. Okay, so hopefully that will be at least give you a little bit better understanding of how we would design a complete mix activated sludge plant.